Well, here in the chain we have another talk. Marcus Leach, who is a radio astronomer from Canada. Let me yes, okay. It's a standstill picture, and Studio Control says that Marcus has been here in connected to us, but obviously there are some network problems right now. It doesn't matter. You, dear audience, you see how Marcus looks like with a standstill picture, and I'm going to present Marcus to you. So Marcus has been involved in high technology development since 1979 and has had an interest in radio astronomy since high school. And he worked in various roles at Nortel for nearly 20 years and was involved in the Internet Engineering Task Force for 14 years, the IETF, having held roles as both Working Group Chair and Area Director for the Security Area. And he began applying SDR technologies in radio astronomy in 2004 and has been a user and contributes to GNU Radio since 2005. In 2016, Marcus created the Canadian Centre for Experimental Radio Astronomy to provide practical tools and techniques for small-scale radio astronomy programs in universities, colleges, and secondary schools. And CCERA has an active and diverse observing program where he's engaged in. And the topic of his talk will be about mapping the sky at 21 centimeters. And here this talk is about GNU Radio in radio astronomy. So I'm handing over the microphone as in control over to my colleagues in over there. Studio Control, please play our pre-recorded talk.
Good afternoon. My name is Marcus Leach. I'm the current president of the Canadian Centre for Experimental Radio Astronomy in Eastern Ontario in Canada. Today I'm going to talk about a project we've been working on with Carleton University to run a dual polarization spectrometer for the 21 centimeter band. And while Carleton uses the data to teach undergraduate students about radio astronomy to compute the galactic rotation curve, we decided that we'd take the same data that we provide to Carleton and produce a heat map of the sky at 21 centimeters. So I'm going to go over all of that in this talk. So a little bit about me. I've been involved in high tech since around 1979. I've held various roles in IT, software development, technical standards, that sort of thing. I was a working group chair in the IETF for a few different working groups. I was an area director in the IETF for 4 years in the security area and assisted with the development of standards like IPsec and TLS and all of those things. Helped shepherd them through the standards process. I hold a bunch of patents in cryptography and network security, mostly through my role at Nortel, but also through a couple of other companies. I got involved in amateur radio astronomy in 1986 on a project to build a 21 centimeter interferometer just outside of Ottawa. And I've been involved in amateur radio astronomy on and off since then. Whenever an opportunity presented itself, I would get involved. A ham radio operator since 1986, and I've been involved in GNU Radio since around 2005, both as a contributor and a user of GNU Radio in my radio astronomy work. I started the Canadian Centre for Experimental Radio Astronomy in 2016. And I've been mostly semi-retired since 2017, mostly focusing on CCERA and doing a little bit of consulting work on the side. So what about software-defined radio and radio astronomy? It has been a long road to acceptance of the technology in both professional and amateur communities, which surprised me. The first paper in the field was one that I wrote back in 2004, New Directions in Amateur SETI Receiver Design. But for about a decade, I was really the only person using SDR techniques in radio astronomy. Professionals weren't interested because the receiver bandwidths were too narrow, and they already had their own custom design hardware to do some of this stuff. And the amateur community at the time in amateur radio astronomy was mostly what I would have to describe as old school people who weren't that comfortable with computers and modern technology. So it took quite a while, but when the RTL SDR showed up, the technology became really cheap. So a lot of people thought, well, why not, try this out in radio astronomy? And so, yeah, about starting around 2014 or so, more people got involved in using the SDR techniques in amateur radio astronomy, and it's been really great since then. So there's been a lot of software packages out there since then. Virgo, the West Virginia University Radio Astronomy Lab has done a lot of work with GNU Radio and small-scale radio astronomy, and of course so has CCERA, and that's basically our mandate, if you will, is to work on small-scale radio astronomy techniques, publish our software, talk about our hardware designs, all of that kind of stuff. The very early versions of GNU Radio, like prior to 3.7, included some in-tree radio astronomy applications, which I contributed to early GNU Radio, but we pulled it out partially because some of the dependencies were unpleasant, but also because it was more of an application than a core functionality of GNU Radio. So it migrated out from there. So yeah, I started CCERA in 2016 for small-scale research and providing observing to support to post-secondary education. We have a relationship with Carleton University, as I mentioned, in support of undergraduate astrophysics. We were located in a small town called Smiths Falls from 2016 to 2021, but we recently have been relocating to a much smaller town about 15 kilometers away from Smiths Falls. So the spectrometer, this is the instrument that basically we describe as our bread and butter instrument. It provides ongoing data to our academic partners, and is used to produce sky maps and compute the rotation curve of our galaxy. The GNU Radio component actually runs on a little Odroid XU4 with an AirSpy R2 as the radio hardware. We support dual polarization, as I mentioned, so there's basically 2 Odroids and 2 AirSpy units. And the Odroid sends integrated spectra via TCP at about 10 hertz to a PC, which further processes and logs the data and so on. So the goal for this work was to produce a 21 centimeter brightness map. So a brightness map ignores the individual spectral components and considers them together all as one brightness level, if you will. And we cover astronomical declinations from -35 to +75. So it's 110-degree coverage of the sky, which is fairly respectable. Given our location in the northern hemisphere, actually the northern part of the northern hemisphere. And the Doppler range we cover in the brightness map is from -160 kilometers per second to +160 kilometers per second. And as I mentioned before, we use ongoing Carleton University spectral data to calculate the brightness over the sky and produce a lovely map. And the other reason, of course, is that people relate more to pretty pictures than they do to other types of radio astronomy data. So it's nice to have a data product lying around that's an image although a very coarse one, of course, given our spatial resolution, that you can show to people and say, this is the kind of thing you can do with radio astronomy. So there's a picture of our equipment. Of course, these pictures are now obsolete since we've moved from that site, but we were using a 1.6 meter dish with 2 LNA modules, and then that would feed over about 60 meters, 60, 70 meters of cable to the receivers that were in our receiver room. And you can see that there. There's 2 AirSpy R2s and 2 Odroid XU4s coming from the antenna. The antenna has a linear actuator on it, and the software moves it every 25 hours to a new declination. And it just keeps doing that all year long, just slowly moving up and down every 25 hours and recording what it sees. And then that data is collated, sent off to Carleton on a daily basis. And then we also use it for our SkyMap. So this is just a quick picture of our new site near a little town called Rideau Ferry. You can see that there's no buildings there, and it's on the ground, but it's actually a fairly nice facility in the science sense because it's further away from any large towns. There's 38 acres, whatever that works out to in hectares. It's like something like 15 hectares. And it's mostly barren and rocky, so there aren't very many trees to get in the way. And so it allows us to do a bigger variety of experiments without having to worry much about whether our landlord would be supportive of our activities and so on. So this picture shows the new mount for the 21 centimeter spectrometer. It's still in progress. We are hampered by weather here, and also the fact that the province I'm in is currently in lockdown, so it's much harder to get work done. So this will be the new mount for the new 21 centimeter spectrometer. We're upgrading to a 2.5 meter dish, keeping the same feed and all the same back-end electronics and so on. And the equipment, once it's all in place, will be housed in a trailer. Rather than a building, although in the future we may put in a permanent building depending on what the site owner allows us to do. So that's a flow graph. It's probably a bit hard to see, and it actually looks much more complicated than it really is because it supports 2 receivers. The reason for that is that that allows you to also do what's called differential radiometry, where you use one channel either as you put a terminator on it or a cold noise source, or have a secondary antenna that points at a cold spot on the sky, and then the other channel is used to compute differences. But this flow graph basically is just 2 copies of more or less the same thing. It computes a spectra, and it also computes the total power on each channel. So just a complex to mag squared, and integrates it with IIR filters. And then it just sends it to TCP sync after it interleaves the data so it can go over a single stream. It's actually 2 streams. The spectra go over one stream, and the other data products, if you will, go over the other. So it's the total power Sobro channel, and the differences go over one channel, and the spectrum goes over the other. And this runs on a little Odroid, and we have just a pretty generic rack-mounted PC that collects this data, as well as data from a lot of other experiments that we do. So we've got sort of a centralized location for the data to live and then get distributed to our partners. And the actual radio receivers are typically on their own little dedicated Odroid or similar single board computer. So what do these spectra look like? That's typical at the site that we're at in Smiths Falls. You can see that there's a spur there, a fairly strong spur in the data, and that is actually a harmonic. It's the 142nd harmonic of the 10 megahertz clock on the AirSpy, and it's relatively strong. So the only thing we could do was actually eliminate it in post-processing and smooth over it. No amount of putting in, filters and, ferrites on cables and all that kind of stuff was able to reduce that spur that much. Of course, the total range we're talking here is only a few dB, so it looks really strong here, but in terms that a telecom person would be thinking about, or a ham radio guy, it's only a few dB out of the noise. So really not that strong in absolute terms, but strong in radio astronomy terms. The little hump in the middle is the spectrum produced by a cloud of hydrogen, that's neutral hydrogen, that's in the beam at the time that spectrum was taken. And the blue lines represent the range that we actually care about. And you can also see that there's a considerable slope of about a 1.5 to 2 dB slope in the data. This is just an artifact of the receiving setup, either in the receiver itself or cabling and so on. Again, in ordinary telecom applications, you probably wouldn't care about that. But in radio astronomy, when you're trying to extract fairly precise data, you have to account for that in your data processing. So this is what it looks like after we've processed a little bit. We pull out the RFI, we've desloped it and normalized it and computed a temperature estimate. The sky temperature estimate is actually based on what we already know about the 21 centimeter sky. We don't have an absolute sky temperature reference that we can use. So we just basically scale our data to existing data sets out there. Like we know what the maximum sky temperature is at 21 centimeters, and we know what the minimum is. So we scale our data according to that. So once we have the process spectrum, we can use it to form pixels in a sky map. So we sum each processed FFT because each individual part of an FFT represents the power estimate over that particular chunk of bandwidth. So the sum is the total power over all of that bandwidth. And again, as I mentioned, we scale it into the approximate range that we know the sky to be at 21 centimeters. So between 15 Kelvin and 100 Kelvin. So the resulting pixels are then processed using Matplotlib. So we do a Gaussian interpolation to produce a smooth image, and we dump that as just a PNG file. And then afterwards, I use GIMP to manually enhance the contrast and the brightness. So there's two different Python routines. Make pixels is the one that takes the raw FFT data and basically grids it into pixels into a 5-degree grid. And then pixels.py turns those pixels into a Matplotlib image. When we move to the new site, our grid size will get smaller because the dish is larger, so our beam width is smaller. So we'll actually be able to produce somewhat higher resolution sky maps from the data. So there's the resulting map, which covers a declination range from about -35 to +75. Actually, this particular map was to +70, but later maps were extended out to +75. once we modified the mount slightly to be able to reach that high. And it looks like a heat map like you'd expect from any other bit of scientific data out there. So the bright parts here are the galactic plane. Most of the hydrogen we're looking at is within the plane of the galaxy, at least within the velocity range that our survey is interested in. Extragalactic hydrogen, of course, is further away, which means it's red or blue shifted a lot more, and it would be outside our spectral window for producing these maps. And this is very similar to other maps produced by other amateurs recently with very similar equipment, which is not a surprise. I mean, at the kind of timescales that humans live, the sky doesn't actually change very much. So there's a list of some GNU radio astronomy software. The website CCERA has their own GitHub account. And we have lots of different bits and pieces of software, including the software that produced this sky map. West Virginia University, as I mentioned, has an out-of-tree module for GNU Radio called GR Radio Astro. That was produced in collaboration with the National Science Foundation. And there is the Virgo software. I can't remember the guy's name. He's from Greece. But he's been working on this stuff as well with a slightly different approach. So Virgo is basically like a Python library that you can pull into your application, from the way I understand it, to do radio astronomy-like things. And that's about as much as I know about it, but it is one of the ones out there. There are several others that I don't know as much about, so I didn't put them here. Lots of little discrete tools here and there, both for GNU Radio and other systems. There's applications written for Windows that don't use GNU Radio, and little discrete Python apps and so on to just pull samples off of a receiver and log them, all of that kind of thing. But these are more full blown, and all three of them are GNU Radio based. And I didn't do a sort of introduction to radio astronomy because of time constraints. But for people who are interested in radio astronomy, maybe doing some amateur radio astronomy, I've got some links here. Radioastronomy.org is the website of the Society of Amateur Radio Astronomers. There's NRAO, which is the National Radio Astronomy Observatory in the US. They have a public website that has lots of really good introductory information, and even course material, which is really quite good. And I've referred to their course material several times for, getting the correct equations and all that sort of stuff. So the NRAO website is actually really useful, even if you aren't a professional radio astronomer. It's got lots of really good information. There's also the CCERA website. We have a memo series and some documents, and we like to document the activities at the observatory on a reasonably regular basis. And so people are welcome to visit that website and look at our memo series. I think we've got around a dozen memos in our memo series. And of course, I'm always working on new ones. There'll be a new one coming out soon about a FRB project that we're planning. That's a fast radio burst, which some people may have heard of. And we have a project on the go to build a capability for detecting FRBs. And that is it from me.
Okay, thank you, Marcus. Very, very interesting talk. And well, radio astronomy is probably at least if I've heard it, the most challenging thing, because you need to work with signals that are further that come from further away than possible on Earth, right? I mean, when radio amateurs are talking about signals, okay, Michael, we have a very distinct experience about signals from Antarctica, which is very remote, but signals from a different star, or from different whatever constellation out there, of course, they're way weaker and way more remote, and that's very interesting indeed. So noise and all those considerations are very important there. Okay, so now we've heard 4 talks altogether on statistical applications and statistical approaches to radio spectrum processing. Very, very interesting. Thanks very much, Marcus, particularly now for your talk. And I'd like to open the panel. And Studio Control told me that we have quite a number of participants here now. Hello, welcome back everyone who's been talking before. And very briefly, we have so many experts here in the panel. I've just opened the round, and please raise your questions to whoever you want to raise them. Please go ahead. Who goes first?
I have some questions collected from the chat for Stefan. Stefan, did you read the chat?
Yes.
Okay. Would you like to answer if you have the questions? I can repeat the questions.
Yes, please.
From Mutsinski, when I worked with neural network, the most important thing was the pre-processing. Without that, for my use cases, I did not converge. Have you just trained on the IQ inputs, or was there any other pre-processing?
So I've just trained on the IQ data. I did remove a DC component, and I also normalized the power such that every data has the same power level, and that's it. You can also do something alternative. Many people are calculating a spectrogram. So they form a kind of image. That's what you usually see in a waterfall diagram, and use these images to do the signal classification. And if you do that kind of stuff, it's basically possible to use a neural network that is suitable for image processing. So you turn this signal classification problem into an image classification problem. And you can also have good classificators with that kind of approach. I personally wanted to know if it's possible to do that without that spectrogram calculation, and to see if the network is able to learn discriminative features just from the IQ data.
Okay,
and the results show that it is possible.
There is an addition. So we want to keep the answers mostly short, if possible.
Okay.
Do you think that the training with more low SNR data will improve the accuracy of the for low SNR input data?
So the SNR here in the data goes down to minus 10 dB, which is already
Yes.
very little. So it's important to have some kind of low SNR samples to make the network learn also about noise. Basically, it has to learn that noise is not a discriminative feature to distinguish between the signals. It will definitely help, but there is also kind of limit. So it doesn't make sense to train a network with like minus 50 dB or so.
Okay, the last question of the same person, Majsinski, I'm not quite sure how to pronounce it. Have you tested your method on a real SDR transceiver?
I've made some basic evaluation. The problem is evaluating a neural network for classification in that application is not that easy, because the accuracy is highly dependent on the SNR you have. So if you have like a real signal, you first have to determine the SNR, and you have to make sure there's no interference and so on. So it's not so easy. But I've made some basic experiments, and it worked astonishingly well. Yeah, so I'm not sure if I can achieve 98% of accuracy, but it's a really useful tool, and I managed to determine modes like Domino X and Olivia, which I couldn't identify just by looking at the spectrum or listening to the signal.
Okay, thank you very much. One question to Markus. Henning Paul, one of our next presenters, which have been active yesterday as well, he said, I'm wondering why exactly that harmonic of 10 megahertz clock is so dominant and not the adjacent ones. Can you give an answer, Markus?
Sure. So the 10 megahertz harmonic is quite strong in that particular radio. The AirSpy radio does have a very strong harmonic at 1420 megahertz. It appears to be very strong, but if you look at the scale of things, the hydrogen signal, if you will, is typically only 1 to 2 dB above the noise floor, and the harmonic of the clock is typically, I mean, I haven't looked at it recently, is typically about 10 to 15 dB out of the noise, which sounds strong, but don't forget that the noise temperature of the front ends of these new receivers is actually pretty low compared to what we might expect in even like a 1990s era receiver.
Okay, thank you. So these are the questions which I collected from the chat. Anybody else?
Well, Markus
I
had a
haven't
question
observed
for me.
the chat.
Okay, well, Markus had
I
a
haven't
question for me at the end of my presentation, and the question was, can it always be better? Well, not using this setup. What I figured out is that although we are amateurs and we use an amateur radio band, we've got several types of usage in the band, and it doesn't really make sense to measure frequency band occupancies mixed up between FT8 CW signals and FM or DMR repeaters. So this would scale up if you have a broader piece of spectrum with the same type of usage. For example, a upload frequency of 4G, for example, to see what's actually happening over there. I hope that answers the question.
Yes, thank you. Interesting. Coming back to those distributed approaches. Referring to the topic we've been talking after the end of Adrian's talk with distributed receivers. So I find that approach also quite interesting because also in reference to yesterday's talk from Barry with the ZMQ blocks, where you can not just receive locally, but you're completely free of a local reference. You can distribute IQ samples all around wherever you want. It just depends on the bandwidth. So is that a possible approach also to spectrum monitoring in the 21 centimeter band in radio astronomy? Would you, Markus, would you do that? Does it make sense to have distributed receivers?
Yes, for a number of different reasons. The local noise environment, of course, will not correlate across multiple sites. So if you're looking for very weak signals, I don't like to use the word signals in radio astronomy because they aren't signals in the usual sense. So yes, distributed receivers make sense just from the point of view of having a completely uncorrelated noise floor and therefore improving your sensitivity. But of course, other approaches you might think of as distributed receivers, like VLBI, for example. And in VLBI, you use the geographic distribution to improve your spatial resolution through interferometry. So that's another kind of distributed receiver approach.
Okay, interesting. Yeah, sure. I mean, you can create a correlation between those two signals, and then, of course, distill out what you really want to receive. I mean, if it comes in at one side of the Earth, it should also come in at the other side of the Earth, right? So
in
it's
fact,
interesting.
With one additionally
know.
receiver, you gain 3 decibel.
Well, depending on whether you're using coherent reception or incoherent. If you're using incoherent reception, like you're just correlating the data post-detection, then you only get root 2 for every doubling of the number of receivers.
Okay. Thank you very much. Yeah, well, my batteries of my monitor ran out of power, so we had a little technical issue in the background. Good. Thank you very much. Interesting insight. Any other questions from anyone? Particularly on statistics. Yeah, Jean-Michel, please.
Yeah, the statistical analysis that we've seen are showing what I would call static estimators like spectra, spectrogram, waterfalls. And with respect to radio frequency fingerprinting, where we are investigating dynamic features such as signal rise or signal fall time to discriminate between the real transmitter and the spoofing transmitter, for example. I was wondering if these classifiers or artificial neural network could be able to adapt to these time-dependent features of the signal, for example, to detect spoofing and some injected signal in the radio frequency spectrum. If any of the neural network developers has some comment about these time-dependent features.
If you want, I can answer. So basically, DARPA, I think DARPA released a big, large data sets of, I think, thousands of transmitters, Wi-Fi transmitters, and ADSP transmitters also. And there were neural networks that can actually fingerprint these kind of devices. Again, based on minute clock variations of different devices and kind of things. But all those setups are kind of supervised setups. So you need labeled data sets. And if you have labeled data sets saying that, okay, these are these devices, and at some point of time you can do spoofing detection, you can do spoofing messages at least. But the problem is like if there is a device that is appearing and to tell what kind of device it is, it might be a difficult task because that kind of expert knowledge is not there in these kind of neural networks. We just learn from the data and from the data statistics, and if it is not there, that expert knowledge kind of things are not there in their network.
Okay, thank you very much. One more question to Adrian. Does anyone have a question to Adrian? Because Adrian has been staying here, even despite his topic has not been into statistical analysis. Do we have any more questions on distributed radios, particularly with this application? No more questions? Okay, thank you very much. And I don't see any more questions in the stream. Yeah, we have one more question in the stream. How long did the acquisition last to map the whole sky? Marcus.
The data represents about a year's worth of observations. Because the instrument is a transit instrument, it can't move in azimuth, it can only move in elevation. So it moves in elevation every 25 hours by a few degrees. And we get lots and lots of repetitions of the same position. to improve the signal to noise ratio. So it took about a year to produce the data for that map.
Okay, thank you very much. That's very interesting. So that's a long time project for sure. And I think radio astronomy is actually a very interesting topic for all radio amateurs. I mean, it's not just about communicating. I mean, we just have those things, those devices standing around, and we're partly consumers. We benefit from well, solar influence to the ionosphere, but we also suffer from things like Mögel-Dellinger effects and all those funny things that come from the sun. The solar system contains a lot of surprises still, and for sure also in the future. So that's an interesting thing, an interesting field of research. And thank you. Big thanks to all of you for coming into this panel. And so this block was very insightful, and I think it's a very active field of research also in the future. I'm looking very much forward next year, and I'm pretty sure we're going to have some talks on this topic again next year also. So I'm looking forward to see you again here next year or in the next years for sure. And then I wish you a lot of fun with the rest of this Sunday. And I'd like to say goodbye to all of you. And then I would like to lead over to the next talk.